The mechanism of a nuclear weapon represents a complex interplay between physics and engineering, creating one of the most powerful and destructive devices ever devised by humanity. The development and function of nuclear weapons involve fundamental principles of nuclear physics, meticulous engineering design, and sophisticated manufacturing processes. This intricate fusion of science and technology has resulted in weapons capable of releasing immense amounts of energy through nuclear reactions, either fission or fusion, or a combination of both. At the heart of a nuclear weapons operation is the concept of nuclear fission, the process by which the nucleus of a heavy atom splits into two or more smaller nuclei, accompanied by the release of a significant amount of energy. The first nuclear weapons developed during World War II, and those used in Hiroshima and Nagasaki, were fission bombs. These bombs used isotopes of uranium or plutonium, specifically uranium-235 and plutonium-239, as their fissile material. The basic principle of a fission bomb is to bring a critical mass of fissile material together in a supercritical state to sustain a rapid chain reaction. A critical mass is the minimum amount of fissile material needed to maintain a self-sustaining nuclear chain reaction. In a fission bomb, the fissile material is initially kept in subcritical masses to prevent a premature chain reaction. When the bomb is detonated, these subcritical masses are rapidly assembled into a supercritical configuration using conventional explosives. One common method for achieving this assembly is the gun-type design used in the little boy bomb dropped on Hiroshima. In this design, a conventional explosive propels one subcritical mass of uranium-235 into another subcritical mass, creating a supercritical mass that initiates the fission chain reaction. Another method is the implosion design, used in the Fat Man bomb dropped on Nagasaki. In this design, conventional explosives arranged symmetrically around a subcritical core of plutonium-239 are detonated simultaneously, compressing the core into a supercritical state and triggering the fission chain reaction. The rapid assembly of the supercritical mass is crucial to the bomb's function. When the critical mass is achieved, neutrons are released from the fissile nuclei, causing neighboring nuclei to split and release more neutrons. This chain reaction happens in a fraction of a second, releasing an enormous amount of energy in the form of heat, light, and radiation. The explosion produces temperatures of millions of degrees and a pressure wave capable of devastating structures and living beings over a vast area. Fusion bombs, also known as thermonuclear bombs or hydrogen bombs, utilize nuclear fusion in addition to fission. Fusion is the process by which light atomic nuclei combine to form a heavier nucleus, releasing even more energy than fission. The primary fuel for fusion reactions in thermonuclear weapons is isotopes of hydrogen, such as deuterium and tritium. A thermonuclear weapon typically consists of two stages: a primary fission stage and a secondary fusion stage. The primary stage is essentially a fission bomb, which provides the necessary conditions to ignite the fusion reaction in the secondary stage. When the primary stage detonates, it creates extremely high temperatures and pressures that are required to initiate the fusion reaction. The secondary stage of a thermonuclear weapon contains fusion fuel, often in the form of lithium deuteride. The intense heat and radiation from the primary stage cause the lithium deuteride to undergo a reaction, producing tritium and initiating the fusion process. The fusion reaction releases a tremendous amount of energy, significantly increasing the weapon's explosive yield compared to a fission bomb. The design of a thermonuclear weapon requires precise engineering to ensure that the stages detonate in the correct sequence and that the fusion fuel is properly compressed and heated. Advanced materials and sophisticated manufacturing techniques are essential to achieve the necessary conditions for fusion. One of the key engineering challenges in nuclear weapon design is the development of the explosive lenses used in implosion-type fission bombs and the primary stage of thermonuclear bombs. These lenses are made of high explosives arranged in a specific geometry to create a uniform implosion. The precise timing and symmetry of the implosion are critical to achieving the supercritical mass and initiating the chain reaction. Modern explosives, detonation systems, and computer simulations play a crucial role in designing and testing these components. Another significant aspect of nuclear weapon design is the development of tamper materials. A tamper is a dense material that surrounds the fissile core and reflects neutrons back into the core, increasing the efficiency of the fission reaction. It also helps to contain the expanding material long enough to allow more of the fissile material to undergo fission. Common tamper materials include uranium-238 and beryllium. The detonation of a nuclear weapon releases not only an immense amount of energy but also produces a range of destructive effects. The initial explosion generates a fireball with temperatures higher than the surface of the sun, vaporizing everything within a certain radius. The intense heat causes widespread fires, and the blast wave creates devastating pressure that can destroy buildings and infrastructure over a large area. But in addition to the immediate effects, the explosion releases ionizing radiation, including gamma rays and neutrons, which can cause severe injuries and fatalities. One of the long-term consequences of a nuclear explosion is the production of radioactive fallout. Fallout consists of radioactive particles that are lifted into the atmosphere by the explosion and then fall back to the ground, contaminating large areas. These particles can remain hazardous for years or even decades, posing serious health risks to populations and the environment. The development and testing of nuclear weapons have had significant implications for global security and international relations. The destructive power of these weapons has led to efforts to control their proliferation and prevent their use. The Treaty on the Non-Proliferation of Nuclear Weapons, established in 1968, aims to prevent the spread of nuclear weapons, promote disarmament, and facilitate the peaceful use of nuclear energy. Despite these efforts, the existence of nuclear weapons continues to pose a profound challenge to global peace and security. The history of nuclear weapons development is closely linked to major geopolitical events of the 20th century. The Manhattan Project during World War II was the first large-scale effort to develop nuclear weapons, resulting in the creation of the bombs dropped on Hiroshima and Nagasaki. In the subsequent Cold War era, the United States and the Soviet Union engaged in an arms race, developing increasingly powerful and sophisticated nuclear arsenals. Throughout the Cold War, both superpowers conducted extensive nuclear tests to refine their weapons and demonstrate their capabilities. These tests, conducted in various environments including the atmosphere, underwater and underground, provided valuable data but also raised concerns about environmental and health impacts. The Partial Test Ban Treaty of 1963, which prohibited nuclear tests in the atmosphere, outer space and underwater, was an important step toward limiting the environmental damage caused by nuclear testing. The end of the Cold War brought a reduction in the nuclear arsenals of the United States and Russia through arms control agreements such as the Strategic Arms Reduction Treaty. However, the threat of nuclear proliferation remains a critical issue, with countries like North Korea developing and testing their nuclear weapons. The international community continues to grapple with the challenge of preventing the spread of nuclear weapons and ensuring their safe and secure management. In recent years, advances in technology have raised new concerns about the potential for cyber attacks on nuclear weapons systems. Ensuring the security and reliability of command and control systems is essential to prevent unauthorized use and maintain strategic stability. Efforts to modernize nuclear arsenals also involve the integration of advanced computing and materials science to enhance the safety, security, and effectiveness of these weapons. The ethical and moral implications of nuclear weapons have been the subject of intense debate since their inception. The devastating impact of the bombs on Hiroshima and Nagasaki highlighted the profound human cost of nuclear warfare. The potential for catastrophic humanitarian consequences has led many to advocate for the complete elimination of nuclear weapons. Movements, such as the International Campaign to Abolish Nuclear Weapons, which was awarded the Nobel Peace Prize in 2017, work toward achieving a world free of nuclear weapons. Despite the efforts of disarmament advocates, nuclear weapons remain a central element of the national security strategies of many countries. The concept of nuclear deterrence, which posits that the possession of nuclear weapons deters adversaries from launching a nuclear attack, continues to influence defense policies. The balance of power and the maintenance of strategic stability are key considerations for nuclear-armed states. The future of nuclear weapons is uncertain, shaped by technological advancements, geopolitical dynamics, and international diplomacy. Emerging technologies, such as artificial intelligence, hypersonic weapons, and advanced missile defense systems could impact the strategic calculus of nuclear deterrence. Additionally, the evolving nature of threats, including the potential use of nuclear weapons by non-state actors, adds complexity to the security landscape. In conclusion, the mechanism of nuclear weapons represents a remarkable crossover of physics and engineering, involving intricate processes and advanced technologies to achieve their destructive power. From the fundamental principles of nuclear fission and fusion to the sophisticated design and manufacturing of weapon components, the development of nuclear weapons is a testament to human ingenuity and scientific achievement. However, the devastating potential of these weapons also underscores the urgent need for responsible management, international cooperation, and efforts toward disarmament to ensure global security and peace. The ongoing challenges and debates surrounding nuclear weapons highlight the importance of continued vigilance and commitment to reducing the threat of nuclear conflict.